Hello everyone. So let's solve this LeetCode hard problem, power of heroes. So the problem states that we are given a zero index integer array nums which represents the strength of some heroes. Now the power of a group of heroes is defined as if these are the indices of the heroes in a group, then the power of this will be the maximum power square into the minimum of the powers. Okay, so it is simply maxi square into mini. Okay, now we need to return the sum of power of all non-empty groups of heroes possible, and since the sum could be very large, we need to return in modulo 199%. So sum of power of all non-empty groups, that means we need to account for all subsets. Okay, all subsets of nums. So what you need to do here is simply we need to go through all the subsets of the nums, and in each subset we need to find the maximum element as well as the minimum element, and we need to take the maxi square into mini and add it to our sum, and we need to return the final sum that we'll get. So for example, here the subset will be, for example, the subsets here, non-empty subsets will be 2 1 4, then 2 1, then 2 4, then 1 4, and finally 2 1 4. So in this case the answer will be simply 2 square into 2. Here it will be 1 square into 1. Here it will be 4 square into 1. 4 square into 4. Here it will be maxi square. So 2 square into mini 1. Maxi square 4 square into mini 2. Maxi square 4 square into mini, which is 1, and here the maxi square will be 4 and the mini will be 1. So this is the mean. So when we will submit all of these values, we will get 141. Hence that is the output here. Similarly, if we have 1 1 1, so we know like the subsets will be 1, then 1, then 1, then 2 ones together 3 times. Okay, this one, then this one, and this one, this one. Okay, so we'll have 3 1 1s, and finally we'll have all 3 ones together. So we know like in each case what we will get, we'll get the answer as 1 square into 1 only. Okay, so this will get, will 7 times, so 7 times we will getting answer as 1, so hence the output here will be 7. So this will be the output for this case. So what can be the most brute force way of solving it? Since we need to find all the subsets of nums and then try to find the answer for that particular sum, so hence we will be iterating through all subsets. And when we are at a given subset, what we'll do, we'll find out the max element as well as the mini element, and we'll update our sum. Initially sum is 0, so we'll update our sum with what? Sum equals to maxi square into mini, and since this may cross long, so we'll get do mod at each step, and this may also means go to long, so sum plus equals to, so we'll do maxi into maxi percent mod, and then into mini, then the overall mod. Okay, and we need to do this sum equals to sum plus, so that means there will be one more mod here. Okay, so that we do not means none of these values exceeds 199 plus 7 ever. Okay, so this will be the approach, simple. And how we'll be iterating through all the subsets? So that is like we have discussed in multiple times. What we do, simply we create a mask of, means the maximum number of subsets, means how will we create a subset. So at each, means if we try to see, so for each element we have a choice of either picking it or not picking it. Okay, so each element has a choice of either being set or not set. Okay, so we can represent it in the form of bits. So what do we have? We have n minus, means total n bits we have, and if all the bits are set, then the maximum value that this can represent is 2 to the power n minus 1. Okay, when all the bits, means all the elements are included. So we can create a mask of 2 to the power n minus 1, and we can go iterate through this mask, means from 1 till 2 to the power n minus 1. And now for each mask will be representing a unique subset. So the set bits in M means will include those indices in subset. Okay, so the set bits in num will simply denote that we are including these indices in our subset, and then based on that we'll be finding out the maximum as well as minimum, and at each step we'll be updating our sum with this. So let's see the code for this approach. So we initialize the mask as initially as 2 to the power n. So we'll give going from 1 till less than a mask, that is 2 to the power n minus 1. Now initially our result is 0. We initialize maxi with 0 and mini with 1 in 9 because the nums of I lies between 1 and 1 in 9. Okay. Now we iterate through the given array. We see like which of the bits are set, means which are the indices are included in our current mask, current M. So we see like if this bit is set in M, that means this element is included. So we'll update maxi as well as mini, and then once we have got the maxi as well as mini, we need to find the maximum square first. Then we need to take the product of maximum square into mini, and then we'll update our result with result equals to result plus maxi square into mini. And in the end, we'll return the result. So we know the time complexity of this will be, since this will go till 2 to the power n, and we have again n, so it will be n into 2 to the power n. So let's see the constraints. So n can go up to 1e5. So this is like this will obviously give clearly because 2 to the power 1e5 is very large and into 1e5. So this will be very large and hence will give TLE as well. And we cannot simply like create this mask as well because like one left shift 100 is simply not allowed. Okay, we cannot store this value. So what do we do now? So we need to like derive some approach which may run in, since it is of 1e5. So the approach should be of the order of n log n, or maybe only n, means something of the order of this approach is expected here. So how do we see? So one thing that we can observe here is, since we need to account all subsets, and the maximum and minimum of a subset will not change even if we like sort the given array. And why sort? Because if we simply sort it in the basis of increasing order, then we know like if we have a current element here, then this will be the maxi for all the subsequences which end at this element, right? Because we'll be means picking some elements from this sequence, and for all these sequences this maxi will be fixed. Okay, so we will only need to see the minis only. So what if we sort the given array and then try to means analyze the problem statement? So let's try to do that. So the first step is to sort the array. Okay, sort the array. Now once we have sorted it, what do we need to find? Suppose we iterate from I till 0 to n minus 1. Now for a particular I, if we are at a particular element x, means x equals to nums of I, what do we want? Means this will be the maxi here. Okay, so the maxi square that we currently have will be x into x. This is sure. Now we need to find all those sums, means all those subsequences which are from 0 till n minus 1, which end at this particular I. Okay, which end at this particular I. So we have how many elements? Total 0 till I minus 1, means we have total I elements on left. Okay, now each of these element has a choice of like either means getting included as a part of this subsequence or not. Okay, and what do we want? Since we know like for all the subsequences which end at this particular value, their maxi square is fixed. Hence what do we require? We require the sum of, means because it will be fixed, so it will be simply maxi square into sum of all minis which end at I. Okay, that means we need to find this maxi square is already calculated. We need to find what? Sum of minimum values of all subsequences which end at I. This is what we need to find. All subsequences which end at I. Now how do we find this value? So we know like we can try since we need to like deal with subsequences, and like maybe we have the choice of either like element can get picked up or not get picked up. So maybe we can use dp to calculate this value. Okay, maybe. So let's try to see like how can we create this dp state, because we know like we cannot store the last element, then the dp will become n cross n. Okay, so we need to do it, calculate this dp in the like state of dp of n1. So now how will be calculating this dp? So suppose we know that we are at this ith index and we want to calculate this dp of I based on some pre-computations till dp of I minus 1. Okay, this is how we try to proceed. So dp of I we want to calculate, and dp of I minus 1 means sum of minis of all subsequences till I minus 1. Okay, till I minus 1, that means it has all subsequences, which means either we can use uh, from 0 till I minus 1, we are able to use 0 alone or 1 alone or 2 alone, or like means it does not mean ending at I minus 1. It simply means sum of all subsequences which uses all the elements from on the left. Okay, because if we want to calculate this SI that we need, sum of all subsequences which end at I, we need to first be able to calculate for dp of I. It means that will definitely be including this nums of I, means nums of I in the subsequence. Okay, so if we have the result from 0 till I minus 1, then if we simply include it, so if we include it, then the result will be extended. Okay, so hence the dp of I will be what? If we include these values, means include this subsequence as part of all those subsequences previously, and we know like even if we include this, since it is greater than all the previous values, that means the mini will not change. Hence the sum of minis will remain the same only. So in this case, it will be simply dp of I minus 1. And what about the case where we start a new subsequence from here only? What about that case? So in that case, we need to account all those mini subsequences which start at this particular I. Okay, so which end at this I only. So it will be simply what? Nums of I. Okay, so this is the case of where we will be able to find the number of subsequences which end at this particular I. But this is what we needed to find. So this is what? This is means dp of I was sum of all subsequences which end at I. Okay, so this we have already calculated. Hence if we are at a given element I, we will able to find the minis which using maxi square into what? dp of I minus 1 plus nums of I, means the sum of all minis. This is simply sum of all minis ending at I. Now for the next, means now we'll be able to calculate the current, means the result ending at current I will be able to calculate. But how will be updating this dp, means to include the ith index such that it stores, means not only ending at I, but all subsequences which include I as well. Okay, that means this dp of I should be updated with, finally it should be updated with what? It should include all the subsequences which means either include end of I, means the nums of I that we had, or like does not include it, means we do not need to only store the values which end at this particular I. Okay, so it will be simply what? It will be simply the values that we have created so far, means the result that we have got till dp of I minus 1, and then plus the number of means subsequences which sum of some mini subsequences which end at particular I. So and for ending at particular I, what was it? It was dp of I minus 1 plus nums of I. So it will be dp of I minus 1 plus nums of I. Okay, so this is how we'll be updating the dp at each step, and it is simply 2 into dp of I minus 1 plus nums of I. So here, like what we needed for each, at each step what we needed only those sum of all minis which end at that particular I. But in dp what will store? In dp will store sum of all subsequences till I minus 1. Till I minus 1, that means dp of I minus 1 till I minus 1, that means we will be able to not only ending at I minus 1, means all those values, either 0, then 1 separately, then suppose 0 1, then 0 1 2, then 2 separately, 0 2, all those subsequences. Okay, and sum of minis of all those values, then only we'll be able to, like if we are at a particular I, then all those possible manners of choosing the subsequences on the left side, then we'll be including the current element in those subsequences. Okay, then it will become dp of I minus 1, and then if we take this element alone, then it will be simply plus nums of I. So I hope like the entire logic is clear. we required two values. One was the sum of many subsequences ending at particular I, and to calculate that we needed a sum of minimum of subsequences before I which has like all the subsequences, means which has entirely all the subsets only. Okay, so these two values we simply calculate, which means this dp will be storing the sum till I minus 1, means all the subsets, and at a particular I will be able to calculate that using dp of I minus 1 plus nums of I. So I hope this is the entire logic of the problem. Let's see the code as well to get a more clear understanding of this. So what do you do? The first step is to simply sort nums. Okay, now the current answer will be 0. Instead of creating dp, since dp of I is dependent on dp of I minus 1 only, so we can simply store a variable only. Now it will represent the sum of minimums of all subsequences before current index. Okay, this is what mini sums will be stored, means denoting here, and we store the mod as 1e9 plus 7. Now we iterate through the nums array, and at each step what we need to find, we need to find the current mini sums. That means we need to find the maxi square into current mini sums. Okay, and what will it will be simply dp of I minus 1 plus x. So dp of I minus 1 was mini sums plus x. Okay, so this is what we do. Now the current mini sums we have calculated, this value we have calculated, the x square will be x into x. Now the contribution currently will be x square into current mini sums, and now we'll be updating our answer with this contribution that we have. Now we need to update this mini sums. That means we need to update this dp of I. So I will be updating it. It will be simply what? dp of I minus 1 means plus the subsequences, sum of subsequences ending at this particular I, which will be simply what? dp of I minus 1 plus nums of I. So hence it will be simply 2 into mini sums, 2 into dp of I minus 1 plus nums of I, 2 into mini sums plus x. Okay, so this is what we'll do, and it will finally return the answer. So this was the approach of like this sorting will take big of n log n, and the space that we have taken, if we doesn't include the space required for sorting, then it will be constant only, and this is, we are doing it big of n only. So this is the most optimized approach for this problem. Let's try to submit the code as well and see how much time it takes to run. This is the same code that we discussed previously, and yeah, it runs in 14 ms, which is very fast. So this was the overall approach for this problem. We first saw how to iterate through all the subsets, and once we were able to do that, then we saw that the constraints are very constrained. So we need to get a solution of n log n or n. Then n log n since we need to handle the maximums, we try to see like if we simply sort the arrays, then the maximum if at ith element it will be greater than all the previous elements, so the maximum will get fixed. Then we simply need to solve the problem of these minis. So for this particular some fixed maxi, we need to find the sum of minis which till I minus 1 and the ending at particular I as well. So we calculate those two values using a normal dp, and once we are able to do that, then we simply iterated through the logic and calculated that values at each step. So I hope you were able to follow along with the approach, and if you did, make sure to like as well as subscribe. And if you yet have any doubts remaining, feel free to comment down, and I will be happy to respond. Thank you so much for watching.